Okay.
One little synchronization clap. 3, 2, 1. Thank you.
Okay. Well, welcome to our September Nature Education Talk, our NED Talks. This is a great turnout. I'm really excited. Joe and I, when we talked about it, it's like, okay, you know, it's kind of a unique topic. Wasn't sure, you know, if this would stir, you know, some interest or not. Obviously it has, so that's fantastic. Very excited to have Joe Hunter with us today. You know, if you haven't met her, the minute that she starts talking, you're going to realize that she's from the UK. And she has a wonderful accent. And I've met Joe, you know, through the Nature Center, through the 5Ks, through other, you know, events and such, and had no idea just what a Renaissance woman this woman really is. I mean, she's got talents that I'm sure have not even been discovered. Materials degree, materials science. Yeah. Yes. And so I had to look it up. I had to Google it because I was like, what is this? And I mean, it's amazing. I'm not even going to go into it. She can explain it, or you can Google it yourself. But fascinating woman. She is here with us today because she makes these extraordinary instruments, the Astrolabes and Nocturnals and things. And she said, you know, what do you think about this with the space exhibit? And I said, we need to bring them in. You need to put them on consignment in our gift shop, but how do they work? Well, bless her heart, she's explained this to me at least 3 times, and I'm just going, I don't get it. I just don't get it. You're going to have to come and tell everybody how to do it and do a demonstration, and then maybe this noggin will, you know, click in, and I'll have that aha moment. I'm sure you all will understand just like that, and it's just me. But anyway, so Joe's here today to do just that. She's going to explain these wonderful instruments, you know, how they've been used for, you know, years and years and years, ancient civilizations, and now we've got, you know, James Webb Telescope and Hubble and all of these things, and these instruments are, you know, giving us all of these photographs. But this is the real deal, and so I'm excited, you know, to learn more about it. So if we'll give Joe a warm welcome.
Well, hello, everybody. Thank you so much for coming. Well, where do I start? Well, let's, after that lovely introduction, who am I and why am I standing here talking about astrolabes? So, my husband, Alan, over there with the camera, and I came over to the US almost 20 years ago. I've done, as Becky mentioned, my degree was material science and technology. I've spent probably 30 years doing aviation photography as a hobby. I've spent 20 odd years doing coding, website programming, that kind of thing. And I've always had one foot in each of the arts and sciences camp. It's always been kind of a dual thing with me. And then, I guess about 4 or 5 years ago, you know, I guess around, I can't even think, was it before or after the pandemic started, when you told me I should buy a laser. and we're all sort of sitting around, and it took me a little bit to figure out what I needed. But I don't think my laser pointer works on here, so it doesn't know. So the one at the end there is me in full aviation photography mode with the long lens. Then we have the big CO2 laser that we bought, and that's in our old house that was sitting in our dining room. Big industrial laser in the dining room. I mean, who doesn't have that? So the first thing I made, continuing with the aviation, was that little wooden Spitfire up there. And, you know, I've got to start somewhere, and you start learning how to use this equipment. And then many years ago, I was starting, I did fused glass for a lot of years, like kiln formed glass. And I thought, I kind of fancy making a sundial for the garden. So I thought, well, I need some software to show me how to draw these things out. So I got this software, and I made the sundial, which you'll see in a moment. And I thought, well, this is cool. And then the software had a way of making astrolabes. And I thought, well, that looks really cool, but I have no way to really make this. And bear in mind, this is still like 10, 15 years ago. And when I got the laser, I thought, I can make those astrolabes. So I thought, well, let's have a go at this. So I started making, that was about the first one I did after some tweaking, which is a single plate, acrylic Rete. We'll get to what those are in a minute. And my basic astrolabe. And I thought, well, this is cool. And if I like this, maybe other people would like this. So I started putting them on Etsy. And apparently people like them. So here we are, 4 years later, and I'm making astrolabes and other things. So let's start with the Lunar Volvelles, which is the only one of the instruments here that really deals with the moon. This is the Volvelle. And a Volvelle by itself really just means anything that rotates. And they used to make these in manuscripts and ancient books, and they would print them on the pages, and they would have little pivot in the middle, and you could turn the paper. These are obviously made of wood. And what these do is you have a calendar around the... I wish my laser pointer was working, but the calendar around the edge is a normal calendar. Then you have a zodiac calendar. This ring here gives you the hours of daylight and night time for your latitude. And these are by latitude, these last two rings, because obviously things change the further north you go. And then this ring here is the solar elevation, the maximum solar elevation for that part of the year. So then you have these two parts in the middle that turn, like this. The sun ring here, the markings on it describe how many days past the new moon that we are. So what you do is you take, for today, for example, what are we, the 18th of September, isn't it? And 20th, is it? 17th. Well, that's close enough. In there somewhere. So you park it on the 17th of September, and then you move the moon ring to how many days past new moon we are. And I've got to confess, I didn't look this up, but I know we've got, actually no, it's the full moon tonight, isn't it? Because we have the eclipse. Yes. So lunar eclipse tonight, everyone. So we must be about here, and in the little window in the middle gives you the moon phase. So it's kind of nice, you can just follow this around the year and keep moving it on every day, and you get the moon changing every day. So, and this graphic is an old graphic, and I'm afraid doesn't have it on, but I did put on the lunar festivals, the solstices and equinoxes on here as well. So it has all those things, you can track it through the year, which is kind of neat. And I think people like those because it relates to the moon, and it's quite relatable, that device. So, moving on to sundials. This is the aforementioned fused glass sundial I made originally for the garden. And these, obviously, you know these, the garden sundials, everyone's seen these. What you may not know is that this part here, the gnomon, that angle, that from the horizontal, is supposed to be the same as the latitude that you're at. So beware, if you go to a garden centre and think, oh, that's a pretty sundial, I'll have that, make sure it's for your latitude, because if you buy it for like 20 degrees further north, and a lot of this stuff comes from the UK actually, so it'll be for 52 degrees, and we're at 30 here, so it ain't going to work. So just be aware that is a thing. And this one also has the curves for the max and min of how far the shadow will progress during the year. It obviously extends in the winter because the angles are lower, and then in the summer it's nice and short. So you have those. Another sort of sundial, this one's the equatorial sundial. And these are basically the same idea, that this is the gnomon. It casts the shadow onto the edge of that hour ring. And then the hours are marked on both sides, so different times of the year you're going to get the shadow falling, visible from either side. This particular one does allow you to change the latitude that you're at. So this one will get you within 2.5 degrees of your current latitude, which honestly is good enough for a sundial like that. You'll see similar examples of this and varying degrees of complexity in people's yards, and the full armillary sphere with all the ribs and fancy looking stuff. Then it's all based on this same idea. And while we're on sundials, can't resist taking you to India quickly. We went to India almost 20 years ago now. Found this fantastic place in Jaipur, Jantar Mantar Observatory, and it was built by a Maharaja in the 1700s. And all of these are sundials. Every single last thing you see in these pictures, they're all sundials. And star dials. These ones down here are actually for different constellations of the zodiac. And they all point to different things, and it was just huge. And there's more pictures at that address on my website there, but I mean, isn't that cool?
Yeah.
Moving on. This is a nocturnal. So here is my ones. And I make these from a dark material with, it's all acrylic actually, this one, with light engraving so you can see it at night, because this one is designed to let you tell the time by the stars at night. So what you do, and I put the instructions on the back, and I'm actually wearing a little brass one here as well. So what you do with this is, let's see here, you've got these 3 constellations. So you've got Cassiopeia, the Little Bear, and the Great Bear, and those are the 3 that you use. And then each 3, you see I've got 3 tabs on here, and this is a calendar ring around the outside, and then you put the tab to wait. So say we're going to use Cassiopeia, and I know this is current at the moment, so you've got Cassiopeia to today's date, so it's about there in September. So sort of moving this over to here a bit, and then you take the device, and it's got a hole in the middle, and you find Polaris, and you hold it up, and you look through the dial in the middle at Polaris, and then you find Cassiopeia. And right now, I know that she's kind of over here somewhere in the early mornings. So you imagine Polaris is like the corner of the top of the screen there, and Cassiopeia is over here, and you line up the pointer with the stars, and it tells you that it's 4:30 in the morning. On this dial here gives you the hours. So, and we'll get to further into this in a moment, but that is 4 in the morning solar time. So it's not what's on your watch, but we'll come back to that in a moment. But that's your basic nocturnal, which is a nice little device because it's relatively accurate, surprisingly, for being such a basic thing, but it's nice, it works. So, what is an astrolabe? Now, a couple of 3 years ago, I had the good fortune to be in London, so I went to the British Museum. They have lots of astrolabes, and they're all really pretty brass ones like that. So the photos you see of those, they're from the British Museum. And it's an analog computer that gives you the timings and positions of the sun and stars, is what it basically boils down to. It's a 2-dimensional representation of the spherical heavens above us. And you can see there, put in the Greek, aster is stars and labein is comprehension. And there's other translations, but that's your basic gist of why it's called an astrolabe. So we'll cover a little bit of history, not too much. So they actually, surprisingly early, like in 150 BC, Ptolemy is out there in Greece, and he's working on what he is now known as the stereographic projection. They didn't call it that, they called it unfolding the sphere. And his works were based on Hipparchus, or Hipparchus, I don't know how you pronounce Greek, I'm sorry. So all these bright Greek guys are coming up with these mathematical concepts and things, and they start figuring out that you can map the heavens with this projection. And then as the centuries go by, the next sort of 500 or 600 years, you've got people writing treatises about it, then they start writing descriptions of how to build them, how they work. Then the Muslims got hold of it and went, this is fantastic for figuring out prayer times, because the Islamic prayers are all based on times of days, shadows, particular goings on in the heavens. So they were like, oh, we're having this. So the earliest one that still survives is from the 8th century, and that's an Islamic astrolabe. And then many more have been produced since then. And they think a lot of the astrolabes in history were made of wood and paper and materials like that, but of course those don't survive, so the ones we have in museums now are all made of brass because that survives. So we have Abu al-Abbas writing his book on the construction in the 9th century with complete instructions for design, and that kind of spurs on everybody to start making them in earnest. And then the whole knowledge goes from Islam through India, North Africa, and kind of curls back round to Spain, where it starts to hit Christianity. So Gerbert of Aurillac, who later became Pope Sylvester II, he brought astrolabes to Christian Europe, and monasteries had them from the 10th century, and it kind of worked its way up through Europe and got to the UK by the 11th century. And Christians weren't so, they weren't as keen as the Islamic people for working out prayer times, so they weren't focused on doing that, but they certainly helped, and that they used astrolabes for general timekeeping and other things that they do, which we'll get to. Over the next 500 years or so, there's refinements, cultural localizations. The Islamic devices were a lot different from the European devices. They have all kinds of different graphs and measurements that they do. We start seeing equal and unequal hours, which, let's pick this one up here. We'll get to this, but the part at the bottom here shows the unequal hours. And back in the day, people they didn't have clocks and watches. We didn't have a rigorous 12-hour day and a 12-hour night. They perceived their days more by way of fractions. So they'd be like, well, there's a sixth of the day left until sunset, or a quarter of the day before the sun, or the night before the sun rises. I'll see you at the 11th hour. But how long was that hour? They kind of increased and shrank and expanded with the course of the year, and the days getting longer and shorter. So that the astrolabe became useful, especially later on, for converting between the unequal hours and clock, regular 12 hours or 24 hours, however you look at it. And then in the 16th century, Geneva, known for its clock and watch manufacture, and it goes way back. They've always been into making instruments, so that kind of heart of Central Europe has always been into making devices such as this. It got very popular. They were churning them out left, right and centre. And then as we get through to the 17th and 18th centuries, we start seeing more modern devices. We start seeing clock towers, and we start seeing pocket watches and all of those kinds of things that now people can tell the time just by going, hey, what's the time? Rather than having to pull out the astrolabe and measure things and look. So they start falling out of use. The Islamic world kind of hangs on to them because, again, prayer times. They like that, so they kept using them, and they may still do. I thought I'd throw this timeline together just to put things in context here. You've got sundials go back to 3,500 BC. The Babylonians are there with their little sticks and shadows. Stonehenge, 2000 BC. People were figuring out the sky way back then. Ptolemy comes along with his stereographic projection. Hourglass is invented in 500 AD, so we're starting to, and then you can see the rest of the timeline that the astrolabes are appearing kind of earlier on, and then the tower clock, which was at Hampton Court Palace in London, the first tower clock, and that came along. It wasn't very accurate, had to be rewound every 6 hours or something. So we're not talking super technical here, but it was there, it existed. And then as things tend to do, they get shrunk, they get more accurate, they get more reliable, and then you've got people, not quite with iPhones yet, but but we're getting there, And then later on we've got Galileo. Hans Lippershey was actually a Dutchman. He invented the telescope in 1608. Galileo comes along and goes, well, that's cool. Let me have a look at that. Makes it 20 times magnification by the next year. So he kind of got on with that and did all the things that Galileo is known for. Along comes Isaac Newton, invents the reflecting telescope, and then people are using these things now to really study the heavens and see what's going on. The sextant, I was surprised how late it was actually, 1750 for a sextant. And that aforementioned Maharaja, he's in here somewhere, about the 1720s and 30s. And then time zones come along in 1884, and we'll get to why that's important in just a sec. And then obviously the modern age comes in, and astrolabes have kind of fallen by the wayside at this point. So that just kind of puts it into context as to how things fall in history. So Islamic and European astrolabes, as I said, they're quite different. Islamic ones are super decorative and floral, and their script, I guess, lends itself to huge amounts of calligraphic decoration. And the one on the left is obviously the Islamic one. This part at the top is called the throne, and you can see the Islamic one's like huge and covered in script, and is just very, very pretty to look at. The European one it's not horrible by any stretch, but it's plainer. They didn't go to quite the degree of decoration that the Islamic people did. Excuse me. On the back of the Islamic one, as I said, there's a lot of different scales and graphs that we just don't see on European ones, and I haven't ever really gone down that road to try and replicate that, because there's really no use for it in this part of the world in this day and age. So to keep things simple, I've kept with the European system of what's on the back of astrolabes. They're very much more calendar based. The unequal hours feature again, and the shadow squares are there, which are used for more. This is the shadow square on the back here, and you can use it for figuring out like heights of trees and buildings, and I'm trying to think of the word, but we'll come back to that. Yeah, that sort of thing. Yeah, trigonometry, that's in the right direction, isn't it? As you can see there, the limb is the part on the outside with the hours. The throne, we just talked about, just the top bit that holds it. The mater is the body of the instrument that holds everything together. The plate is usually interchangeable. The one I'm holding actually is a single plate device, but that's no big deal. The ruler is this part that moves on the front. The alidade moves on the back. And the rete, now obviously back in the day they didn't have acrylic and fancy things like that, so this is definitely a modern invention. But the wooden rete, like this one here, that's kind of more like the traditional sort that you find in museums made of brass. So it allows you to see what's going on behind the different points point to the different stars. So whereas on here it's kind of hard to see probably from back there, but the stars and constellations are engraved, so you can see much more what's going on because you can see the whole constellation drawn on there. Whereas these have like the brightest stars from each constellation is just literally a point. So you can, but it works the same way. Now on the rete here, that scale exists on both sorts, and that's really the key to using this. And this is an exploded one that came out of the museum. You can see the rete on top made of brass. These three things here are all plates. There's the mater in the limb and the alidade at the bottom there. Now, I mentioned about the stereographic projection. I'm going to have to introduce you all to what that is. So here is a diagram that tries to explain it. So with an astrolabe, everything is projected up from the southern hemisphere. So you've got the Tropic of Capricorn, the equator, and the Tropic of Cancer. The white rings there are what's drawn on here. So you can see how they project. So the Tropic of Capricorn ends up being the outermost ring, and then that's kind of where are we at here on the plate, and then that's the outer one, and then the equator is in the middle there, and the Tropic of Cancer in the middle, and then the stars get projected in, and I put Orion in the middle, which is a complete lie because it's actually out here somewhere, but it gives you the general idea. So in relation to the plate, there they are on the plate, and you can see Orion's down there. But there's the three main rings, and that's how it sits on the plate itself. So the plate markings, you need to know what's going on here. The North Pole is here in the middle. The horizon line is this one, number 6. So that line there changes, it's the bottom of the visible sky. And then under here is the hours, the unequal hours. The top is what you can see in the sky. So lines number 1 there, 1 is the North Pole. 2 is the zenith above your head, so directly above here. The North Pole is usually over there somewhere in our skies at the moment. So you've got a difference between the North Pole and the zenith above you. Then you've got the, where are we? 8 is the altitude circles, so that's the rings around the zenith here. And that's how many degrees up in the sky it is, or any object. And then the azimuth circles are radiating down and around. So they are like the slices of the orange around us. And the degrees of the compass as well. So that's north, and then you've got the degrees of the compass either side, east and west. The plates change a lot with latitude, so this is why you always want to be buying an astrolabe that relates to where you are, or buy one that has multiple plates that you can change out for where you're going to be. You can see 25 degrees, that's down in Florida, and 55 degrees is up in Canada. And you can see how much that changes. And on the equator, the horizon line would be completely flat along here. And then at the North Pole, it would be a complete circle. And you can see these grayer lines, I don't know how well you see the difference there, but those 3 lines there are the twilight lines. And when you get past about 70, 80 degrees, they really don't go down. And you know how in the North Pole the sun never sets? Well, those twilight rings go all the way around and they never disappear. So it's true, it doesn't set. So turning to the back of the instrument, you've got all the calendar scales on the back, and this is the other side of where the magic happens. So the outer circle here is the quarter circle degrees, which is more used for when you're sighting objects. So if you're sighting the sun or stars in the sky, then you'll just read off from the edge how far up it is in degrees. The second one in is the ecliptic longitude. That's the important one. So as we go around the sun in the course of the year, then it's really just one long month, you can think of it. We have, our normal calendar is 12 months, and we have 1 to 30 something days, give or take. The ecliptic longitude is just 1 to 360 all the way around in the year. And the starting point of that is March the 20th. That's 0, which is the spring equinox. And that's the point where the sun moves from it moves across the equator at the spring equinox. So that is where they decide that's where the ecliptic longitude is going to be. The signs of the zodiac are really just historical. So it used to be that people would use these a lot more for astrology than they do now. But the Rete traditionally was marked with the signs of the zodiac, so I kept those there because a lot of people refer to it, and it's nice to know where you're at. But it's not really you're not really working out anything astrological with these devices. It's purely another calendar. The zodiac divides the sky into 12, and each day of the zodiac is just another calendar. Actually, I'm going to skip back just to here. I just want to make a note about stellar precession, which I forgot to mention earlier. Now that means as we go around the sky, or around the galaxy, once every 23,500 years that we go around the whole galaxy. And Earth also has a bit of a wobble in its orbit. And between those two things, it means the stars move. You don't think they move, but they do. And they move 1 degree every 71.6 years. So that means that all these points on all those lovely brass astrolabes you see in museums, they're in the wrong place. Because they move. And it's like, you know when you see those photos that people do of long exposure at night and you get all the star trails? Imagine that on the Rete and all the stars have moved around a bit. So every time you've got an astrolabe that's a few hundred years old, everything needs to be shifted around a bit. And I'm told that if you find sometimes an old astrolabe and the points are bent, it's because people have tried to kind of jig them. Okay, another little interlude. Time. Now this is something important, because we didn't used to have watches and we didn't used to have time zones. So historically, every town, during the course of the day, the sun would get to its highest. That was noon. Perfectly logical, right? Mm-hmm. Every town has noon slightly later than the next one, because the sun obviously moves around the earth, and every degree is 4 minutes difference. So along come the railroads in like the 1800s, whenever that was. And they think, well, we want sensible railroads, and we're going to need timetables, and we're going to need ways of unifying those timetables. We better have time zones. And then they came up with this idea of, we're all so used to it now we don't even think about it, but there are the time zones, and they're each based on 15 degrees of longitude difference. And so where you are in the time zone makes a difference, because the sun is going to hit over here a lot earlier than it hits over there. And, excuse me, you need to calculate for that. And there's another thing that you need to calculate for, and that's the equation of time, which is a modern addition to the astrolabe rear, and it's this kidney-shaped curve that lives on the back here. And you won't find this on older instruments, but more modern ones, there it is. And that's because the sun will go back and forth about 15 minutes because of our elliptical orbit around the sun. During the course of the year, it shifts. It's not quite where it's supposed to be, so you have this kidney-shaped curve that allows you to read off what it is. Now, on the back here, you've got an equation of time scale on the alidade, so you can read off from the curve what the correction is, plus or minus 15 minutes. So between where you are in the time zone, the equation of time, and daylight saving time, you can see over 90 minutes difference on what your watch tells you. And this is the same true for sundials as well as astrolabes, anything using solar time, which is pretty much everything here. Here we are in central Texas at this time of year, and right now we are seeing about an hour and a half's difference between solar time and clock time. So you need to kind of factor that in. And once you figure out the correction for your location, you can just remember that. And then you just need to look up the equation of time. So, you want to learn how to actually use this thing? We'll start with the easy one. Finding sunrise and sunset. And what you do, you start on the back, and you find out what today's ecliptic longitude is. And here we are. I'll show you on the example there first. The 25th of August is about 154 I've got here, which might be a little, yeah, we'll call it that. So you're finding that on the back on the scale of ecliptic longitude. And then on the next one, the ecliptic longitude is the same as this circular scale on the Rete here. So you rotate the Rete until 154 lies on the horizon line. So remember, the horizon is the bottom line here. And it's kind of hard to see on this one, but it's there. So where 154 on this scale crosses the horizon line, you move the ruler to that intersection, and then you read the time from the edge, which says about 5:40, 5:35 solar time. And then that's eastern side is sunrise. And if you want to know what times the sun sets, you just move the whole lot round here. And you read off 6:30 solar time is when the sun will set. So sunrise, sunset. And then if you want to do that for today, let's just do that for today. What did we say we were? The 18th, 17th? Thank you. I think I'd remember. So we're at 175 degrees of ecliptic longitude. So 175. 175. Bang on 6 o'clock solar time is when the sun will set tonight. Which is going to be about 7:30 time. So in fact my watch here says 1936 actually. Sorry, 1938 is when the sun will set tonight according to Apple, so that's close.
So what's the adjustment now? It sounds like about 70 minutes.
At the moment, yeah, it's off that order. I haven't worked it out for the exact location here, but I'll give you a sneak preview of a link I'm going to put at the end here. Where are we? There's a wonderful app called Solar Time, and you can cross-check it. So right now, my watch is telling me it's 1:41, and it says 12:10 on Solar Time. So it says that, 90 minutes and 39 seconds is the current offset. So this is dead handy. But just sanity checking.
Joe, I'm sorry. Can you tell us again what the difference between solar time is and our time?
So it's the difference between when the sun is overhead. So on our clocks, that's saying, in fact, this is actually not bad because that we're 10 past 12 solar time at the moment. So the sun is just off from noon solar time, but my watch is telling me it's 20 to 2. So the difference is because of where we are in the time zone and the equation of time. So we're probably, let me hop back to that time zone map.
And daylight savings.
And daylight savings, yeah. So we're over here. So the time zone, if it's based on 90 degrees, then we've got to be at least 40 minutes off. If it's, is that right? 1 degree, 4 degrees.
4 minutes per degree.
Yeah. So we're probably, what are we, about 100 degrees longitude, aren't we, here, I think? 9900?
Yeah, 99.
So yeah, I mean, you're seeing that kind of, in fact, mean solar time. This is telling me minus 36 minutes on here, so that's the answer right there, is the difference in minutes between the time zone official longitude and our longitude over here, because the sun takes 40 minutes to go across, or 36 minutes to move that distance. So that's why you're not seeing noon at noon. It's somewhat later for us. Does that make sense?
Yes.
Yeah.
Thank you.
So does that mean that if you were right on the line,
You should see a zero offset if you're right on the line, yeah.
if it was not summertime?
Although that for the equation of time.
Apart from that, yeah. Yeah.
And daylight savings.
Yeah, I mean, the equation of time does go to zero, I think-ish. I guess about 4 times a year. So, yeah, you can play with the marker. There's 4 days in the year where it becomes zero. So, if you were on that 90-degree line on those 4 days of the year, that should be completely zero. But otherwise, yeah, you've got some working out to do. Right, where do we get to? Okay, so we did the... So is everyone happy with finding sunrise and sunset?
Mm-hmm.
Okay. Okay, star rise and set. So sun's fine and all, but what time is Betelgeuse going to rise? Because I want to
Jinx it
photograph
3
them.
times.
Dare you. So, you put your star. All right, we'll use Rigel then, shall we? We'll put Rigel on the horizon line. So here's Rigel on the horizon, sitting there. And then we go back to the ecliptic longitude as before. So what did I say today was 175?
Yes.
174.
174.
Yeah. So Rigel go. Rigel is there. Actually, I was talking about him rising, wasn't I? So let's put him there. So he's over here now, because he's going to rise. And I find 174 on here, which is about there, which is about 10 minutes past midnight, is when Rigel will rise. So if I move the whole lot over to there, he sets at, well, about 10 minutes before 12. Midday. So you've got, and Orion is a morning constellation at the moment. So I don't know if anyone's been observing the Jupiter and Mars paths across the sky. They had a wonderful conjunction a few weeks ago, and Orion is sitting just off from where they are in the early hours just before sunrise. So yeah, that does figure. So that's how you find star rise and set. And obviously that works for any star, any object on here.
Can you also find the moon's rise and set times?
This does not deal with the moon at all, because it moves too fast, and nor does it deal with planets, except in a small limited capacity, which we'll get to right at the end. But no, the moon just moves too fast. The only thing I've got here that deals with it is the Volvelle that I showed up front. So, okay, finding the current time. So, you can do this in day or night, which is a bonus over the nocturnal, because that only works at night. And that only works in the northern hemisphere as well, because you need Polaris to look at. Anyway, I digress. So, if you're looking at the sun, obviously don't look at the sun. Looking at the sun is bad, so we use the shadows. So, you've got the sights on the back of the alidade here, and you hold it up so it's straight. This is why it's got a dangly string, so it holds straight. And you go to the sun, and it's not going to work too well in here, but imagine the sun's up there and you've got the shadows casting down here, and you get as accurate as you can. It's a little bit tricky. Obviously at night, if you're looking at a star, you can look straight through the sights and look at the star and get perhaps a more direct reading. But once you have your elevation, then you use that elevation to see where your ecliptic longitude meets that elevation on the plate. So, supposing the sun was at, say, 50 degrees of elevation at the moment. So, we take the 174 and we go to there. And obviously you've got two options for this. You've got a morning and an evening or afternoon option. So presumably you know which end of the day you're at. So in the morning, where that crosses the 50-degree line is about 10 in the morning. And in the afternoon, where do we go here? That one. It's about 2 in the afternoon when the sun's at that elevation. Now, I'm not saying that's the time now because I can't measure it from obviously in here, but that's how you do it. Is you basically take the current elevation of whichever object you're looking at, and you put today's ecliptic longitude where that crosses the elevation line, which is the ones that go round like this. Then you read off the time, and that's your time. So it's actually fairly simple to do, but it just takes a couple of steps. And also, if you're looking at stars or sunrise or whatever, then where you have this intersection of lines, it gives you where to look for the object as well. Because where the intersection happens, you follow the lines that radiate out, and it gives you the compass bearing on where that object's going to be in the sky. So you know how high it is, you know which way around where it's going to be, you can get a bearing on that object right there. Okay, I don't know how many of you have come across planispheres. It's basically a map that shows you what is going to be in the sky at any given time of night, and you can use this as one as well. So this does require you to know what the solar time is, and maybe you've just worked that out, or maybe you just know. So if the ecliptic longitude I've got on the screen there is 189 and the solar time is 1935, so you basically take the ruler, you put it on 189, which is there, and you move it to, what did I say, 1935? So you just move it around, so you've got the ruler on the ecliptic longitude, and you move it to the known time, and then all these stars above the horizon, that's what you can see. So right now, or for that example, you've got Arcturus there, you've got Altair, Pegasus is up, Vega, all the good stuff. And then supposing, going back to my photographic roots, if I have a picture in mind and I want to take this lovely landscape over here, but I really need the sun to be up there, just to be hidden behind that tree and cast the light the way I want it and all the things, then you can figure out when that's going to be. So back in the day, when I first started making these things, I made them as the software spat out the information, which on the plates on the back here has meridian-based markings, and these mean that it's minus 180 at the bottom and 0 at the top. And then later on I realised, or I read around the subject some, and it became obvious that that was actually just a convention, and there was more than one convention, and you can have 0 at the bottom here and 180 at the top, which matches up with our compasses that we use in daily life. So I switched the plates, but this is an old one. So let's go for this one. Yes. Which has the modern markings on. So this is actually one that has interchangeable plates, and actually it's got the more modern sights on it as well. So right, so back to this photo. So 220 is here, and 40 degrees is there. So we move this around to here, and that tells me that where this crosses the intersection of 220 and 40, if I've got this right, actually I think it's there, is an ecliptic longitude of 330. And if we go to the back, we can look at the ecliptic longitude of 330, which is here, which is about February the 17th. So, and you've also got another option here, because the sun obviously goes back and forth in the year. So you can go the other way, around October the 20th. The sun would also be in the same spot. So
did you use that for your picture taking?
I haven't yet, I must be honest. I need to find the picture first. But you can do this. So there's two spots in the year, because obviously we go back and forth with the sun's motion during the year. And it would give you the time as well. So it's telling me for that last one, it's about 1:40 in the afternoon. The sun would be there on that day, in that particular spot in the sky.
Assuming it doesn't rain.
There is that. But then you've got another chance later in the year.
Or you can use Topaz AI.
Well, you could do that. But that would be cheating. And they didn't have Topaz AI back in the day. So yeah, this one's just saying as well that you can read the time, and you've got the two options in the year. Okay, so another little bit of astronomy knowledge for you. Right Ascension and Declination. Now, who knows about this? Anyone? You do?
Well,
You do?
tracking satellites.
Okay, cool. Right, so for those of you that don't know, it's basically the lat and long of the sky. So it's a unified convention adopted by astronomers all over the world that allows you to say where sky objects are. So it starts, the right ascension starts at the aforementioned March 20th spring equinox, and it's divided into, the sky is divided into 24 hours, and it goes around to the east. And then the declination is the elevation up from the equator. So the little globe in the middle here, that's us, and then you've got the sky, and then all the things in the sky are marked with this right ascension and declination. So to find those coordinates of any objects on here, you use the ruler basically. So if I want to find Altair, for example, you put Altair on the 0 hour at the bottom. So these are marked in 24 hours. 0's down here. You put Altair there, and then you just swing the ruler down, and that tells me that Altair is about 9 degrees of declination. And then rotate the ruler to, you leave Altair where it is, that's right, and then you rotate the ruler to 0, which is over here in this case, and you read off the hour, so it's about 19 hours and 50 minutes of right ascension for Altair. And those coordinates, they just stay. I mean, that's where Altair is in the sky. Now, planets, obviously, they have right ascension and declination, but they move. You can add objects to the Rete. If you're going to add a planet, use a sticky dot that you can take off again. Or if you've got an acrylic Rete, use a Chinograph pencil, that should rub off. But what you can do is you can say, well, where is Saturn? I want to see it on here. I want to be able to work out when it's going to rise and set. So at the time of writing, which I updated this the other day, so it should be fairly accurate, Saturn is currently at 23 hours and 10 minutes. So you rotate the Rete so that 270 points at that time, which is kind of weird, but it works. So you take 270, and 23 hours and 10 minutes is there. So I've got the 270 mark pointing down here. And then you put the ruler on the western horizon and locate the declination on the ruler. So for the other day for Saturn it was -7, so it's going to be about there. And planets are pretty much always on the ecliptic because that's where they live. So the ecliptic circle here, you're going to find the planet there somewhere. And obviously this is no exception. So that you can then mark Saturn on there, and then you can use it in the normal way for finding rise and set and seeing when it's visible. And obviously that works for any sky object. Now the moon, going back to your earlier question, was I guess it just moves fast. You could do it, but it would be fast. And it'd be out of date in like an hour. So your mileage may vary on that one. Okay, we're getting there here. So variations of an astrolabe. It's not just this. Southern Hemisphere ones. So they basically work exactly the same way, but everything's reversed. So you've got east-west is reversed, north-south is reversed, and then all the stars are different because they got different stars down there. And I'm told that it was pretty rare to find a historical Southern Hemisphere astrolabe. I know there are at least 2 down there because I've sent one to Australia and I sent one to New Zealand. So there's at least 2 down there, but they are not common objects by any stretch. But they do exist and they work just fine, and they can be made. So it's kind of weird to you make a Rete and it's got all the different stars and it's like, oh, that's very strange and looks funny, but that's what they have down there. So
what did the sailors use?
Sailors. Well, that's a good question. I mean,
15, 16?
That is a good question that I do not currently have the answer for.
Sextant.
Well, sextants didn't come on until later on,
Yeah.
so they're like 1700s before they appeared. But they had Mariner's Astrolabes, which are very much cut down versions of. They had big holes in, and they were heavy, made of heavy metal with holes, so that they would hang and not be swung by the wind. But all they had was pretty much the elevation markings, so they didn't do a lot of what this astrolabe does. But it would be enough to get elevation, like sight readings of the sun for elevation, and then they can work out things from there, I suppose. But yeah, what they did in the south.
And in the Southern Cross, that was about it. Right.
Yeah, the Southern Cross isn't quite in this right south pole, though,
At a
is it?
certain time.
Is it?
And it points to
Yeah, I'm not super familiar with the southern sky, I'm afraid, so not. Yeah, I can't really answer that one at the minute. It's a good question, though. I would like to know now. Okay, so that is a universal astrolabe, and I happen to have one here. Here it is, and this is the Saphea Arzachelis, which was developed. A couple of three guys were instrumental in making variants of this. I think this is the Rojas one. You can solve, it's got a normal astrolabe on this side, normal-ish anyway. You've got the Alidades on this side for sighting because it's only got so many places to be. It's missing a lot of the stuff on the back, like the equation of time and the shadow square and all that. But on this side, you have an attempt at being able to convert from different latitudes. And it's too much to go into here. I don't want to confuse you all, and I'll just confuse myself, quite honestly. But this scale allows you to convert from the three coordinate systems mentioned there. Give you a brief idea. You've got a line here for the ecliptic, and then you've got a horizon line that goes straight across. And you take a reading, or you want a measurement that's on a particular scale, and then this is called the brachiolus arm. And then as you move it between one thing and the other, the arm moves on the scale and it gives you the other coordinate reading. So I do have a page on my website which goes into detail on how to use these if you're interested, but that's kind of beyond the scope for today. But they do exist, and they are for perhaps the more advanced user. The scales on here, they don't mark the scales because you've got three different coordinate systems, and if you put all the markings on, it would just be a sea of numbers. So you have to kind of know which ones they all are, and it sort of makes sense when you use it. The little numbers across there are hours. Yeah, it's a topic for another day if you're really interested. And then you've got things like quadrants, which I've yet to delve into properly. I did make a couple. And this is like a little cut down, folded up astrolabe. If you take this and like fold it that way and then fold it that way, you end up with a quadrant. And again, I've made one of these with the intention of learning how to use it. I haven't quite got that far yet. But the idea is that you have these little knobs up here are the same as the alidade on the back for sighting. So you would sight the sun, the shadows would come down, and then the string is supposed to hang down and give you the reading of the elevation that way. The little bees there are supposed to be able to move, so you can mark positions, and these are a work in progress as far as I'm concerned, but I wanted to at least bring them and show you what a quadrant looks like, so you're welcome to have a look at those. And here's some useful websites. I can send an email out to Becky and she can pass on to anyone that wants these links. That's the screenshot of the solar time that I showed you earlier. There's the website at the top is a web-based version of that. It's a bit of a clunky interface, I warn you now. You go in there, it says, "You don't exist," or something. And you plug in your location, it goes, "Okay, there you are." So it's kind of weird, but it does work and it's free, which is good. No adverts. The Sky Live is nice. It gives you all the current goings on in the sky, so you can find out right ascensions and declinations of things if you want to look them up and just see what's all. It's a really good website. You can spend hours on there. The NOAA link further down, that gives you both true north and magnetic north, which is real handy if you want to set up a sundial, because you're supposed to point them north. I probably should have mentioned that. And you have to, the idea with the gnomon pointing at the right angle, it's supposed to point to the North Star. So you want to know where that is, and in the daytime that's hard. So you've got to point it to true north, not magnetic north. And that little web app, and you can pull it up on your phone, and it shows you exactly where true north is. And then at the bottom there, for anyone that wants to bite the bullet and actually get one of these things, then that's all the instructions for all of my instruments. So that should hopefully fill in any gaps that I may have made today. So with that, I must thank you, and if you have any questions, please shout. Yes, sir.
How did the flat earthers, people who thought the earth was in the center of the universe, how did those theories survive with these instruments being around for so long before a lot of people were convinced?
Your guess is as good as mine.
Good question, yeah.
I'm sure they just do it to wind us all up.
We've got the Julian calendar and the Gregorian calendar.
Uh-huh.
When, actually, I know you talked about the time, the clock tower, but when did they decide that time was going to be used? When did we say
as a clock
specifically when we're going to use a clock, and how did they all get together to do this?
That is also a good question, and I haven't got to the bottom yet of when they really converted or decided that unequal hours were going to be superseded by regular hours. Because you're right, somebody at some point must have said, well, this is crazy, why are we doing this unequal hours? And maybe it was just as simple as that, because it's hard to know in the summer when it's like an eighth of an hour through the seventh unequal hour. Like in 2 weeks' time, that's going to be different. So maybe it was people just like it a bit more regular.
Yeah.
I do know an Englishman named James Harrison.
Okay.
Won a prize. I used 50,000 pounds back then.
Oh, for his clock?
For his clock.
Yeah.
That's why Britain ruled the seas, because he was able to find the longitude.
Yeah, that was a huge deal back then.
He got a clock that could accurate time on a fishing ship.
Yeah.
Before it was just a pendulum.
Oh,
So it wouldn't
yeah.
work.
That was a
figured that
huge
out,
deal.
You knew how far away you were from high noon as your port.
Yeah.
So you could determine your hours, minutes, away.
Yeah, and you could. It was the whole longitude problem, wasn't it? Finding exactly your longitude at sea.
And that's why you guys knew where you were.
Yeah. No, that was a wonderful invention when he came up with that one.
That watch is as big as a piano.
Yeah. Oh yeah.
Have you studied at all how the instruments, how people figured out that this spot would correspond with reality, and therefore I'll draw this line or this curve in this particular spot on this instrument? Have you studied that at all?
I have books that go into that, but I haven't delved into it too much myself. But there are ways of, I mean, it goes into the stereographic projection and how they actually do measure and how they visualize it all. So yeah, I mean, studies have been done, but I have not made them myself. So, but I have books that can explain. Anyone else? Yes,
Is
sir?
the slideshow on the website?
Not yet, but I can put it up there.
Thank you.
Uh-huh. I'll put it up along with the rest of my instructions.
This quadrant with the strings on it reminded me of a sextant. Do you know how to use a sextant?
I do not know how to use a sextant, but I do have a friend that does, and he owns one, so maybe I'll have to go and pick his brain at some point. So I am on a Facebook group that deals with sextants, and there are, a buzzing group of people out there that are keen on these things and they know about them, but it's not something I've ever used. I'd like to though. They look good. But you have a book about this thick, full of tables that go with them. So you have to be able to look up. I'm not exactly sure what they're looking at, but things that you have to know before you can take the reading. So it's not just the instrument; it's this weighty tome that goes with it. So.
How to.
And then I have one more question. These little pointy things that the people used to bend.
Yeah.
That's because of precession?
That's the precession, yeah.
Does it
so
ever come around where it would be correct again?
In 23,500 years, maybe.
So you never bend them back?
No.
We're all going to come back for that.
I do actually have one more thing to show you. So I bought a new laser a couple of 3 months ago, and I've been learning how to use it. But this week, for the very first time, I have made a brass astrolabe.
Oh, beautiful.
So if you want to have a look, it's there. It's a little bit bendy, so you don't need it. But yeah, so I'm quite pleased with those. So, any more questions?
What would they, back in the day, would they use wood?
They used wood a lot, yeah. So these things just don't survive time. You know, wood, paper. That's about all you could use, I suppose, back then. They didn't have plastics, obviously, so there was none of that. But yeah, they just don't survive the centuries.
When did they start making them in brass?
About the 9th. The earliest one was the 8th century. So they've been around a long time. So
How did it occur to them? I mean, just the mechanics of making one.
that is a good question, and I don't know what metalworking was like back then. I've seen texts that say that you would make the brass disc and then literally just scratch it, etch it in by hand, and they were probably doing that because they didn't have lasers.
How would they cut?
Just with a, I don't know, how do you etch brass just with a...
Yeah, I don't know.
Steel.
Yeah. If you make it thin enough, I mean that one there is quite bendy, so it's only 1 mil thick and it's
Steel
millimeters.
with the hardened steel scribes. So.
Did they have hardened steel back then? So yeah, you can
Is
do
it
it.
heavy, the brass one you just made?
It's heavier than the wooden one, so
Yeah,
you know,
I think.
one of each to compare and contrast.
Yeah, I think there would be a lot of weight. Yeah, there's the wooden.
Okay. Wow.
Anyone else? Any more questions?
Yes.
Yeah. That's amazing.
You came all the way from England?
No, I live here in Kerrville.